It's like with the video recordings for Canvas here that I make through Zoom. Sometimes I'll go over there and they're there. Like I'll do something like right after class because I want to do it, or else I'll forget to do it. Download them and upload them to YouTube, and I put the link into the addendum calendar. But sometimes, I mean, it'll be an hour later and they're still not there, and that's happened once or twice. So you never can tell when it's going to happen. Just the nature of the way data gets done. But generally speaking, after the due date, won't show up before then. The only exception for that is in the O2O class. As you do them, they show up, because in that class, there's no due date. The due dates are all at the end. So some people are going to read a rude awakening, but that's the way that one's set up. But on here, everything has a due date, so that's when it goes over to Canvas. But I guess it is. Because Canvas and Alex have to talk somehow. They got to get together and all that, and no telling how long it takes. All right. Anything else? Anybody got anything else interesting? All right. Well, let's get back to variation. We talked about this simple measure of variation called the range. The range is simply the difference between the highest and lowest values. And back in the olden days, before we had all these computers and stuff, this would be a lot more useful. And it's even useful now for explaining things to people, because I tried to pick out a useful example here. The range is just the difference between the highest data value and the lowest. And on this one for San Francisco, the highest was 63, the low was 15, and that's a range of 12 degrees. In other words, throughout the year, their temperature changes between, there's no variation more than 12 degrees up and down. Very simple. You look at New Orleans, where there's some more extreme temperatures. And these are average temperatures, because I know 82 is not the high I would expect, because it gets to the day, and this is averaged over a month, years and years. But anyway, so 82 minus a low of 51, and that one is 31. So there's a 31 degrees difference that the temperatures bounce throughout the year. And if you don't like a lot of variation, if you're a person that likes a even keel like me, someplace like that, like Hawaii or San Francisco, has nice, good weather like that.
Here is their minimum.
Minimum M.
All right. So what the standard deviation is that we're talking about, it basically is just how spread out the data is. So you can see on these three different curves, the orange one is it's kind of skinny, and the red one is a little bit less skinny, and then the blue one is lots less skinny. So those are all what we would call normal curves right there, normally distributed data. See, it's symmetric on both sides of the x-axis kind of thing up in the middle. If you cut it in half like a face. Well, but what this standard deviation measures, it just kind of tells us how fat that thing is. And that's very useful, because it can tell us some things about the data. Most everything we're going to be working through in this is going to be, like this. We don't need to identify it, but they're going to tell us that it's normally distributed, so that, because that's the condition for doing these things. Now, here's where it starts to get a little bit complicated, because there are two different standard deviation calculations. And to make matters worse, they're only different by one small little thing. And it's sort of like those puzzles we used to have in the Sunday paper where you'd have two cartoons and it was spot the difference. Can anybody spot any differences here between this one and this one?
The denominator.
Y'all call out the, yeah, okay. Differences. I'm going to write them right here. So, denominator. Good. Anything else?
The x minus x and the numerator with the symbol above the x.
Yeah, in the top, it uses, it's called, we read it as X bar up at the top. All right. X bar versus that little thing down there that looks like a U, that's mu. Those both are that's both the mean. So for that, that's calculated exactly the same way we saw, but that's just, it's got a different symbol for the sample. And that's really the only difference, besides they call something different. And so the third difference would be the name. S means sample standard deviation. And sigma, which is what that bottom thing is, sigma means population. All right. So there's the differences right there. But the main difference is really just this right here. Now, n means the same thing that it's meant throughout our textbook. N is the number of elements. All right. So here we're going to have a data set. And so we count. And so for the sample standard deviation, the one thing that's different is we got to subtract 1 from however many elements there are in our set. For the population, we don't. Now, there's a reasoning behind that. If you're interested, it's very simple. Because we're dealing with a sample, we've got a potential for error because we don't have the whole set. So the n minus 1 kind of shifts the margin of error, I guess, to err on the side of caution. So that's why that's there. So when it's a sample, you subtract. For a sample, subtract 1. All right. 1 from n. So that's really the only difference. All right. Now I'm going to try to do one of these on here. It's a little bit of a tedious thing. And then but I need to get a nice white board here. I think I'm just going to use, because the Google board's going away. So let's see if I can just go into Google Documents and open up a blank thing, because I just want a white screen. Yeah, that should do it, be enough. Because some of those whiteboards, they don't, let's get a little bit more. Anyway, I'll just use this, see how this works. Because I want to just have plenty of white area to draw things. I don't want all that on it. I guess I'm just going to go back over to the Google Jamboard. It's still there for a while. See, it's going away. Want me to back everything up. But almost none of these, they, oh, that's right, you can't edit them anymore. Oh, well. Anyway, we still got more room on here than anything else, so I'll use this. All right. So what we do to do the standard deviation is we have to, I thought I could get all that out. I can still do it though. All right. So I'm just going to draw a little grid here. All right. I don't like the way that Alex does it. They do it horizontally. If you like it, understand it, all the better to you. All right. So our data set was what? So we're finding the sample standard deviation. Okay, there we go. So find the sample standard deviation. Now, what we got to know is we got to know a couple of things. And the first thing we need to have is we got to have the mean. All right. First thing I'm going to do is I'm going to write these going down like this. Like I said, it takes most of the work is being careful and being neat, which is never a bad idea. I just been doing things on computer so much that it's easier to usually type them. That's the best way to do it for me. Now, over here is going to be x bar minus the x bar, because the x bar is the mean when we're talking about sample. And then this is x minus x bar squared. And it looks complicated like this up here, but don't get too upset. Now, what we got to do is find the mean. So remember, that's 8 plus 10 plus 13. That's probably just shouldn't have a space. All right, and then I'm going to come back and put a line. All right. Oops, not there. You're still out there?
Working hard.
Okay. All right, what does that numerator add up? Has anybody figured that out yet? Otherwise, I got to jump on the calculator. So 54. Divided by 6. What does that give us? So it's going to be 9. All right. So it's a tedious calculation because it takes you through pretty much everything that we've learned so far. So now we're going to take, and I'm going to type it in just because make it a little bit better. So it's 8 minus 9, which is equal to -1. This one is 10 minus 9, which is equal to just 1. So this is 13 minus 9, which is equal to 4. Y'all following this?
So far.
It's just a process. Not doing anything fancy. Just subtraction now. After I find my mean. Okay, 6 minus 9, which is equal to negative 3. And so also is this one, 6 minus 9. All right. So those right there, you don't need to know this, but they're called the deviations. That's what that x minus x bar means. It just means how far is this value from the mean? The mean is the middle. Now, what we do over here is we square each one of these. So negative 1 squared is equal to 1. And I got to write a little square up there. All right. So this one is just 1 squared. And that's equal to 1. And the reason why I put the parentheses around that whole thing is because if you square anything, positive or negative, you always have a positive result. So this is right here is 4 squared. I'm going to try to write it real quick. This is 2 squared, which is equal to 4. And then these are both going to be the same. So this is negative 3 squared. Which is equal to 9. And negative 3 again squared. Is equal to 9. All right, and I probably should have told you this over here, but a good checkpoint, because you see how there's a lot of tedious steps. It's easy to make a mistake, and you wouldn't want to do this whole thing and realize you had a mistake way in the back. Well, let me show you this. These right here, the sum, and that's what that little doohickey means, will always be 0. Because these are the distances from mean, so they're going to balance each other out. Because with that, see, you've got 7 positive and 7 negative, so that's equal to 0. Now over here, that's not going to happen, but we need to know what these are here. So we add them up. So the sum of these is also so it's 1 plus 1 plus 16 plus 4 plus 9 plus 9, which I believe is 40. 40. So these sum up to 40. Sum up to 40. All right. So that's the numerator for the so that's this numerator here. See, which that's why we got to go through all the steps, and that's the most complicated part. All right. So that's that numerator. All right. And so this is what I got. I'm just going to write that formula out with what I know now. So S is equal to And then up here we got 40. And down here, it's n. So n was 6. And since it's a sample, we got to subtract 1. So this is the square root of 8. All right. The square root of 8. And that's something you can approximate on the calculator because they probably ask you to do that. Pay attention to where we rounded off. Let's say we're going to round off to 2 decimal places. So 8. Where's the square root button? Oh, there it is. So 2.83. Because you're almost always going to have to approximate these by rounding them. So pay attention. All right. So that's the whole process for the finding the standard deviation. But before we move on with this, I'm going to ask one important question, because over here, let's see. I don't want to erase that yet, but I want to go back and show you that other formula. All right. I'm going to copy this. So I'm going to ask this question now. I'm going to change it slightly. Where's my thing at? There we go. All right. So I'm going to put this here. Actually, I don't need to put all that. Suppose we find out that the above is the population. How does that change this? Okay. So now we find out that it's a population. So we're going to just make one small change. All right. And back over here in the notes. And what I'm going to have to do is I'm going to go ahead and erase this part if I can without erasing. Because we already got the important stuff over there. And then I'm going to scroll up now. And we want to look at this one. So here, what's going to happen now if I find out that it's a population, as I said over here? All right. Then that means that we now got sigma. And like I said, that symbol is not important so much. It's just that's what it is called. And as I said, is for your work, you don't have to remember. You just need to remember that population standard deviation has the n underneath it. And the reason it has it underneath there is because if you got all the population, you know how much you got. So then here, oh, and you know what? I forgot to put the square root over it. I mean, I did it, but I didn't just pull it out of the hat. It's part of the formula. So then here it's still going to be 40. And down here now, the n is just going to be the 6. All right, so let's run that through the calculator. So 40 divided by 6. And let's see if we take the square root of that. I really should have the Alex calculator. So it gets smaller, see, 2.58. And generally, like I said, why that happens, and you're not always going to do them on the two, treat both data sets like population and sample, but it just to show you that when it's a sample, it's larger than it is for the population. Just to err on the side of caution. Bigger is better. All right, any questions about that standard deviation stuff? That's the most complicated thing here.
Yeah, lots of questions, but it will hold up the class.
Yeah, well, just if you got something, go ahead. I mean, were you talking about on some of the calculations?
Yes.
That time. I'll just take you through the process because it's really the same one for both. So what we're doing is, what that means up at the top means we got to have the mean, and we got, what in the world? And so what we got to do is we got to find the mean, which is what we learned to do in 12.3. So I didn't really, I did that pretty quick, but that's what that is right there. We cover something that we've already, kind of formally gone over. I'll generally go over it a little bit quicker, but that's the mean. And then we subtract, and I'll tell you what, somebody's got a good thing out here. Because a lot of people do it the same way I do. We're just going to show you. That one looks like it's too crazy. Let's see if we can find a good one. Yeah, that was too complicated. What in the world? There we go. So I'm trying to find one that looks very simple. To show you the process. And like I said, this is why I like to do it with a table. But I was trying to find one that just showed the whole process. And then I can explain it by using some better graphics. Because mine, like I said, it doesn't look as good as I'd like it to.
Is this a little bit more like statistics will look like?
This is statistics. So this is what statistics looks like. I mean, and here's the kind of the downside of it. Okay, this is the way that you get it when you first get statistics. You basically doing it is like number crunching stuff. In other words, it's calculations that are very difficult to do by hand, and I'm showing you by hand. But there's an easier way to do it with, technology. And we don't spend as much time on that technology as I like to. But this one right here breaks it down. Is what you got these values, and then this is the mean. So it's the mean of this whole data set. So you're subtracting each one of these from the mean. And then that gives you what's called the deviations. And then you square those. and then you add them all up, and that's the numerator on how we found this 40. Except ours were, a lot smaller numbers, a lot more even numbers. And then once you do that, depending on whether it's a sample, because if it's a sample, then we're subtracting by n minus 1. So we divide by 5 to get the square root of 8, and then that was 2.83. And if it's a population, we would just keep it as the total number of pieces of data that we have. And then do the exact same thing. Divide the 6 into 40, and you take the square root of that, it's 2.58. Like I said, it all comes from these two formulas here. Sample means that you subtract 1 in the denominator, and essentially that's the only one that matters. All the other stuff is labeling. The mean, the X bar, is the same X bar, the same mean as for the population. You just take the mean of your data, subtract it from each one of the data pieces, square those, add them up, and that's the numerator. It's several steps. Now, I will show you when we start reviewing for this some things that Alex can help with. But right now, when I first go over something, I kind of like to go over it by hand. Because especially you get into statistics, and some people there are, really, really strict on doing things by hand.
You teach
All right.
statistics?
Sometimes. Yeah, I like to teach it in a lab, and like I said, yes, and it's certain things I would do if I had control. But since we all got to do the group final and the midterm, I can't have a whole lot of variation. But I try to integrate as much technology as I can, and that's why I like to have it in a lab. I also like to do that with this class too, especially for the second half. Lab helps.
And I'll get your opinion on some stuff after class, if you don't mind.
All right. All right. Now, I'm sure people have heard some of these, most probably the term percentile shoved around because everybody's got kids, and they, when schools give tests, they big on comparing things. Well, that's what percentile is. If we have a percentile ranking and we're in the 80th percentile, then as you can see there, that blue person is got 80% of people below him. So in other words, if it's a test, like a standardized test, then someone who scores in the 80th percentile scores 80% better than 80%. Doesn't mean they scored an 80%. It means they scored 80% better than 80% of the other people taking the test. All right. Now, if we had percentiles are parts of 100, and so if we lived in a perfect world and all of our data sets had 100 pieces in them, then we could just, if we wanted to find the percentile, like the 25th percentile, we would just sort all the data and count up to the 25th person, and they would be the 25th percentile. But data is not like that. Data is often irregular and different sizes and shapes. And so what we're looking for when we're looking for the 80th percentile, we're looking for what person would that be. Here, this person is identified for us, but let's say we want to find the 21st percentile to start, and then the 63rd percentile. All right, now I kind of got these worked out, but I'm going to try to illustrate a bit as we go. But we've got some data here, and I think it's 19 pieces of data, which that's kind of on purpose because it's an irregular number and doesn't have any factors. So, like I said, it'll make this kind of a more interesting process. Like I said, if it's even, then it's kind of almost no fun. All right. Now, we've got those 19 pieces of data. So in order to find the percentile ranking, we go back to the idea of how we calculated the median. And remember, when we calculated the median last time, we had to rank the data. If the data is not ranked, then we cannot proceed to find one of these measures. And the median is one of the quartiles, is what it amounts to. The quartiles divide, and I'll just explain what a quartile is. It just means instead of dividing into 100 pieces, we're dividing into 4 pieces, a quart, a quarter, a fourth quarter of a football game. You know, it's 1/4 of the way through. 2 quarters gives us a 1/2. That's the median. That's the halfway point. And there's 2 more quarters after that. That's what a quartile is. It just breaks that whole data set into 4 pieces. We're not really worried about that here yet, and we just wanted to talk about what they are, just to contrast them with percentiles. In Math 203, the statistics, the quartiles play a part there. But anyway, the first thing we got to do is order the data, lowest to highest. And then, as I said, the N is 19. In other words, there's 19 pieces of data. All right. So if you forgot what N was, 19 pieces of data. Okay. Says N equals 19, but like I said, yes, I'm a visual learner. So if I have something pop out like that, it would help me kind of remember, because I could just remember, I'll be thinking, well, N, what does that N mean? Well, it just means there's 19 pieces of data. N is N throughout this whole textbook. That's what's interesting about it. In chapter 2, when we introduce the sets, the number of elements in the set, that N with that set inside of it just means count them. Same thing in probability. You're counting. And then here we're counting. We're using the N here in our calculations. Now, if we've got 19 pieces of data and we want to find the 21st percentile, all right, then what we're going to do, /21st percentile, and this is where it helps to know how to go back to decimals, because I only know one way to like multiply, and a percentile is just a percent. And I know that there's calculators that may allow to do it. So if you are able to do that, that's fine. But this is the way that I know how to do it, is I just do it as a decimal, in other words, because 0.21 is the decimal equivalent. And so by just doing that, and like I said, it makes it simpler to me than the way I look at ALEKS, because I think they keep it as 21 and then they multiply and divide by 100 or something like that. It's the same thing. Like I said, it is. At some point, you got to account for that 100 when you go back and forth from percent to decimal. All right. And just to show you, and I still haven't learned my lesson enough to bring out the ALEKS calculator, but this one should suffice. All right. 19 times 0.21 gives us 3.99. And I got that right here. Okay. 3.99. Now, 3.99 is not going to tell us much because what this refers to, it refers to the location. I believe I showed you in the calculation of the median. For the ones that you look at, the small data sets, you just order them and it's easy to see the one that's in the middle usually. But there is a formula for it. So likewise too here, and that formula tells you the position. Well, see, this right here is kind of in between, but that's not going to do us any good. So what we do is we bump this up to the next whole number. Whoops. Bump it up to the next whole number. And so that gives us 4. Well, that does not mean that the 21st percentile is 4. It means it's the 4th position. So I'll put here the 21st percentile is in the 4th position. All right. So what's the 4th position? 1, 2, 3, 4. There's the 21st percentile. So 21% of this data set is to the left of that 17. That's what that means. Likewise, if we want to do the 63rd, we do the same thing. We do 19. So this right here is the the 63rd percentile. We multiply 19 times 0.63, and I'll do it over here on the calculator. 19 times 0.63. So 11.97. So again, we're going to bump it up. We always bump up. This is not rounding because we're just looking for the position. It's sort of like one of the things you have to do in statistics sometimes is if we want to identify the number of people we would need to have in a survey to get a certain accuracy. Well, if you do the calculations, you could partially come up, well, you need to have 25 and a half people. Well, you don't have 25 and a half people because if you cut a person in half, they wouldn't be able to be in the survey. So you got to take the whole person to bump you above the amount that you need. Statistics is all about being safe, be above and beyond what you need. So that's why we bump up to 12. We bump up to 12. See, we bump up. That's kind of my word. It's actually called a step function, I believe. If you got any portion of a number, but that's what it is. I mean, if you got any portion of a number, it bumps up. See, it always goes up, always goes up. So the 12th position is the home So the 12th position is where the 63rd percentile lives at, okay? So 12. So this was 4, 5, 6, 7, 8, 9, 10, 11, 12. So this, as I said, is 22 is in the 63rd percentile. All right, does that make sense? I got plenty of time to go back over it. Even if it's just a fuzzy kind of question. You ever have a fuzzy question? One time I was talking to another teacher and I just told him I wanted to talk to him about something. When I got to him, I said, well, I can't remember what I was wanting to ask you. So I just kind of asked him a few kind of not so well thought out things. And he was able to point me in the right direction. So that's kind of what learning is about. So the purpose of this is just to find out how much of our data meets a certain criteria. All right. So let's look at this. This is an actual question from Alex. One that they like a lot. So that's why I put it here. Because they're big on asking word things to see if you understand. So that's what this is designed to do. All right. So last year, over 8,000 students took an entrance exam at a certain state university. Justin's score was at the 13th percentile. Isabel's score was at the 21st percentile. Now, I'm going to draw out something that's very rudimentary that kind of represents 0 to 100. All right. So that being said, about right here, kind of put it in the quartiles just for perspective. So this is 50%. This is 75%. And this is 25%, okay? And then this is 100%. Okay, so what we got to do is I want to pencil in where these other folks are at. Let me make them a different color. So right in here, I was trying to get a different color. All right. And then I want to make the other one right about here. All right. So right here, this is Justin. There's Justin. So there's Justin. And then here's Isabel. All right, so this is 13th. And then this is 21st. All right, so now this will help us answer this question or these questions. Which of the following must be true about Justin's and Isabel's score? So let's go through about each of these. Isabel answered 8 more questions correctly than Justin. Do we know how many questions are even on this test, whatever this test is? There's no information about the number of questions on the test. Now, they might be tempted.
Excuse me, Mr. Cruz.
What's that?
Can you tell me why I'm keeping Mark absent for your class? I just got a notification about me being marked absent.
Oh, I don't know. Because you might not have been here when I was called a roll. I
I've
do it
been
at the
here.
beginning for this class.
Yes,
right.
both classes.
Okay.
But it
Well,
didn't tell me
just stick with me after class on that, because
okay.
it doesn't pertain to everybody, I mean, I'm not trying to believe me, I do not use the grade book to ever punish anybody. I mean,
Okay,
I
I
do
just
not
wanna be
care
sure.
about the thing is, but I gotta turn in records. They want to know, and I don't want to spend all day, doing that stuff. So I do it at the beginning, and sometimes if people come in late, I do it. Do that. But like I said, it's not that important as far as to be. I'm not hurting anybody for that. Believe me.
Okay.
Oh, Mr. Cruz, yeah, thank you for letting me know that, because I was trying to connect and my phone died when I was trying to connect to your class for this
Mm.
one. Yeah. Okay. Thank you.
All right. So now, Justin answered 8 more questions correctly than Isabel. Well, again, we don't know anything about the questions. We don't know what they were. But here, these start to be interesting. Now, the 50th percentile is the median here. So this is the median. All right. The median is 50%. So the next one talks about the median. So that we know about. Justin and Isabel scored above the median. Now, the above the median is over here. Okay. All right. So are they above the median? No, but they are below the median. Okay. See, they are down here. So that's one thing that we know. Let's see about the other question. Which of the following must be true about Justin's score now? We're just looking at Justin. We're just looking here. Justin got about 13% of the questions correct. Again, we don't know the structure of the test. Like all those ACT tests, you know a general structure, but you don't know how many they're going to be on there. Maybe there is some way of knowing that, but that's not what the percentile ranking means. The percentile ranking means where you scored in relation to everybody else. So on this one, no. We don't know how many questions he got. But here's one that's promising. Justin is in the top half of all the scores. Is he up here? No, he's down here. So not that one. And this is the same kind of thing. They're taking advantage of the idea that there's a 13 there, and we're so used to compliments that 13 from 100 would give you 87. But again, we don't know how many questions were on there. That's not what the percentile ranking is about. The percentile ranking is about where they appeared. So Justin scored lower than 87% because he did better than 13%, but he had a long way to go to get to the top. And a matter of fact, that's where the 87% comes in. 85% is up here. From here to here for Justin. So from here to here for Justin, that's 87%. All right. Down here is 13, and there's 87%. So that is what we know. That's what we know. Oh, what happened? I forgot. I thought I was thinking that was an Alex from it, but this is just the thing out of Alex. All right. Any questions about that? All right. All right. So let's see what else we can get through in 15 minutes. I was thinking I might get through the whole thing and then we do something after the test, but probably I'll just lecture on this last part. Yeah, we'll just finish up this little piece thing they call the empirical rule. All right, get out a little bit early because I know there's some people that might have questions. Even though Kendra, I'm looking at the darn roster. I mean, I see your name in green there, so I don't know what you're going on about. I'm not seeing something. All right. All right. So just to kind of make a long story short, everything we're working with in this class, and usually most basic statistics classes, is what we call normally distributed data, or the way Alex likes to use the term approximately symmetric or approximately normally distributed. They'll tell you that. Okay. So when you see that, it's just a formality. It just means that you're going to be able to do what I'm going to show you. But it has this kind of shape. And that was the idea behind the histogram. And if you do a histogram, you can more or less look at that histogram and tell if it's normally distributed. And this normally distributed data, I mean, it applies to a lot of data. So that's why it's so useful. Most data ends up being normally distributed over time. And if you got normally distributed data, then the mean, median, and the mode are equal. And that's why, the median, as I said, it's in the middle. Now, this is the thing that we're going to look at here, called the empirical rule. It's just a very basic way to look, because we talked about standard deviations, and this is not so much about calculating the standard deviations, because the calculation of it is just a number crunching thing. And I'm sorry that you got to do it by hand. But what the standard deviation is what's more important here. So if we have this whole graph, you can see that in the middle, at the high part, where down at the bottom, you got the mu, which means the mean, median, and mode thing right there in the middle. That on either side, it's symmetric, and you got 3 hops on each side. 3 to the positive side on the right, 3 to the negative side on the left. Now, what the empirical rule tells us this, if we have normally distributed data, then one standard deviation on either side of the mean, positive and negative, is about 68%, and that's what's in red there. Going out 2 on either side is 95%. and then going out 3, which is about as far as you can go on either side, you get 99.7, which is practically all of that data. And this is when we got data that fits that shape. We know those 3 things by just this fact. And we can also look at like this, that it's broken into halves and what, but see, there's your 68 broken into 2 and stuff. So this will help us answer these questions. All right. So we got, it tells us that the distribution of SAT score is scaled to be approximately bell-shaped with a mean of 500 and a standard deviation of 100. All right. So what I'm going to do here, I'm not sure I'll be able to fit it in here. I'll try to write it. All right. So it tells us that the mean of the SAT scores is 500. All right. And then standard deviation, and that's what each one of these is, simply adds 100. So that's 600. And then 700. And we're only going to go out to 3. So the last one is 800, because each one of those is a standard deviation. And it adds 100 to our 500. Now remember on the left side how they were negative. So that's 400, 300, and 200. So all we're doing now is just applying our kind of personal situation here where the mean is right smack in the middle, 500, and then each one of the hops on the standard deviation, 3 to the left, 3 to the right, 100 each time. And we're just showing it there graphically. Now we should be able to answer this question here. The 68% of scores are between, and here's the 68%, here and here. Because there's a 68%, and we wrote in. So the answer is 400 and 600. Now remember that 2 standard deviations is the 95%. So that's here and here. So for 95%, it's 300 to 700. And the last question is, if we have a score of 700, in other words, if we're right here, we are in the top what percentile? That's what that's asking, the top percent. So, well, there's 2 different ways to do it. We can add all of these up here, or we can use our complement rule. And I'll do that real quick with the calculator, and we'll pretty much be done with it. So that means that we're in the 97.62 percentile. .6. Well, we just say 0.7, we round it. 96.7%. Let me just type it in. I think they wanted it, when they do it a percent, they do out to 2. All right. So we'll talk about this next time. It probably won't take the whole time. I'll try to slow it down for you. And we'll try to we might do some other stuff. Stick around if you got questions.